Hey, let's take a look here at section 8.1, Systems of Linear Equations. Okay, so yeah, we've been solving equations for a while now, and now we're going to up our game here a little bit, and we're going to solve sets of equations. So we can think about things that we've already done before. So if I want to solve this, we know how to do this, right? We solve for x. And we do the usual stuff. You know, we're going to move all the x's to one side, right? We can add that to both sides, and we would end up having 3x equal, if we subtract that 1 from both sides, we got a 1. And then solving for x here, we would have 1/3. Okay, great. Now think about what this is doing graphically. So if we think about these as individual objects, we say, all right, when is that object equal to that one? So this is maybe on a graph, we can draw a picture of y equal 2x plus 1, and we can draw a picture of that, right? So 2x plus 1, this is going to be a line, right? We're going to have slope 2 and y-intercept 1. So it goes through this point here, and then we're going to go, up 2 units for every 1 unit we go to the right, and we're going to go down 2 units for every unit we go to the left. So if I want to draw a line there, boop, there it is. And we can draw the other one. Maybe I'll use a different color here. So if I wanted to draw y equal 2 minus x, well, that's going to be a similar picture, isn't it? It's going to have y-intercept 2, and we're going to have slope -1. So we're going to go down 1 unit, right 1 unit, down 1 unit, right 1 unit. And we can draw our line here. Okay, and these appear to intersect where x is equal to 1/3, right? Which would be this point right here. Now, what we might want to know is what's that y coordinate? Well, if we know that these are going to intersect where x is equal to 1/3, that means that they're both going to have the same y value there. So we could just plug this value in to either one of these lines and find what that y value is. So let's do that. Maybe we can use this one. So y is going to be 2 minus this x value. That x value is 1/3. So we can say what that is, right? 2 is 6/3, so this is going to be 5/3. Okay, and the picture kind of looks like that, right? Split that up into thirds. And then 5/3 would be 2/3 more than 1, so that's about somewhere in there. Okay, so the point is of intersection here. Intersection is the point 1/3, 5/3. So yeah, we've done this before, and maybe we haven't exactly thought about it graphically like this, but we've definitely done these tasks before. Like for example, where is a parabola intersect a line, or maybe problems like yeah, problems like that, right? We've seen this before, and that's okay. So we remember that a linear equation in two variables, which is what we just looked at, where we have the x's and the y's. It's an equation of the form this, where our a's here are real numbers, and so is c, and at least one of those a's is non-zero. So we got to have either an x or a y involved. Okay, so in general, we classify equations as conditional, identity, or contradiction. We've got examples of these, right? Conditional, this is maybe like 2x plus 1. Yeah, 2x plus 1 equal 4. And we can solve that, right? So this would be x equal 3/2, right? If we would subtract that 1 from both sides and divide by 2, we would have this. Conditional equations are true under certain conditions. here specifically the condition that x is 3/2, right? An identity, these are equations like maybe like this, maybe like, yeah. Well, if we would go and solve this, we would multiply those through. So we got 2x plus 4 equals, well, on this side we'd have 2x plus 4 as well. And now going to solve these, we would want to combine our x's. So subtracting 2x from both sides, we just end up with 4 equals 4. And that's always true, right? So something that happened here is the variables dropped out and we're left with a true statement, right? So that's always true. So when the variables drop out like this, what that means is that the value of the variable doesn't matter at all, and it's just always going to be true in this case. Now, a contradiction is going to be sort of like that, but as you might guess, it's never going to be true. So here's an example. If I had 2x plus 4 equals 2 times x plus 1. So if we do the same thing to solve this, we would multiply through. We got 2x plus 4 on the left, and on the right-hand side, we got 2x plus 2. We would subtract 2x from both sides and end up saying 4 is equal to 2. That's clearly not true, so, never true. So more or less, when the variables drop out, we're either going to be left with a true statement or a false statement, and we call them identities and contradictions accordingly. Okay, we're going to have something similar with systems of equations, but we'll get there in a minute. So a system of linear equations in two variables, we've got a set of linear equations that we're going to consider at the same time. So solutions to systems have to be ordered pairs that are solutions to all of the equations in the system. So yeah, an example would be what we had above, right? We had y equal, what did we have? 2 minus x and 2x plus 1, 2x plus 1, and we had y equal x minus 2. Or was it 2? So usually we'll put a little bracket there or the brace to indicate that we've got a system. But yeah, we've got two equations with both of them have two variables, and hey, it's a system of equations. And we can find a solution, right? We found the solution above for this one, and it's what made them both true. Okay, so we're going to have some techniques to solve systems of equations, and we've already seen them in different contexts. So for this one, we can talk about substitution first. Well, if I'm going to have a solution to this, x, y, as an ordered pair, whatever this number is, that's got to be the same number there, right? So the substitution method, we can choose, if I call that equation 1 and then call that equation 2, if I solve equation 2, so solve, gosh, that's frustrating when it drags like that. So we're going to solve equation 2 for x. So we can do that, right? X is equal to 2 plus 3y. And now I know that this x right here has to be the same as that x right there. So I can plug this in or substitute, right? Substitute to equation 1. So I've got 2 times that x value. And now, hey, I've got an equation here that has a single variable, and we can go solve for it. So we do, right? We can distribute this 2 here. We got 4 plus 6y plus y equal 1. Continuing on here, collecting our like terms, we'll have 7y's over there, and we have a negative 3 on the other side. So then we have y equals, negative 3 over 7. And now that we have this guy, we can plug that one back into one of the original equations. So let's put into maybe, it doesn't really matter here. Why don't we put it into the first one? So we've got 2x plus that y value that we just found That has to be 1. And now we can decide what, what that x has to be. And we can just solve this in the usual way, right? We're going to add 3/7 to both sides. So 3/7 plus 1 would be 10/7. And then dividing both sides by 2, we would get 5/7. And then we would have our solution. So our solution is the x value and the y value that it's paired with. Okay, great. And when we're done here, we ought to take our solution and we ought to plug it back into both of these original equations and say, hey, does it actually make it true? Did it actually work? Okay, so substitution. We went and took one equation and we solved it for one of the variables, and then we just plugged it into the other equation. And there we only had one variable left, right? And we could find that one. Okay, good. So that's substitution. The addition or elimination method. Now this is going to rely on something that we know and we've seen before. If I've got two numbers that are equal, they're equal, so one is the same as the other, I can add a third number to both sides and it's still the same, right? As long as this number here, well, if it's anything, I can add anything to both sides. As long as I'm adding it to both sides, we're staying balanced, right? It's staying the same on both sides. Well, what we've got in a system is we've got two equations. So I've got that A is equal to B and C is equal to D. Well, if these two are the same, well, why can't I add C to this side and add D to that side? And now that's still the same, isn't it? Or equivalent? We're adding the same thing to both sides of an equation. So another thing that we've known before, or known from our past, is that if I've got two things that are equal, they will remain equal if I multiply them by a non-zero constant number. So now this is equivalent to what we started with, the original A equal B, right? Multiply by a non-zero number. So moral of the story here is that if I add this side of the equation to this side of the first equation and this one to this one, we're going to come up with an equivalent equation, right? So if we can add these together in such a way as to eliminate one of the variables, well, that's the task here. So we can, if I call this 1 and I call that 2, we can add 1 plus 2. And what do we get? Well, 4x plus 2x is going to be 6x. Negative y plus y is going to be 0y. And then we're going to have 2 plus 5 is 7, right? So we just added those together, and now the y canceled out, right? There's no more y. It's 0 y's. So we've got 6x equals 7, and x is equal to 7 over 6. And we can just go ahead and solve that in the same way that we did below here. So just like that previous example, we can take this number here, this 7/6, and we can plug it into either the equation 1 or equation 2, and we can find that y value that goes with it. Okay, so something that's, we're going to practice this just a little bit, but in practice, we're going to do something a little bit different than this. It's going to be called Gaussian elimination, and it's going to be using kind of both of these ideas together. So let's look at a few where we're going to use the convenient method. So if we've got two equations, two variables, we want to do what's convenient here. Okay, so with this, what do we want to do? So we could do substitution here. And it was probably easiest to take that second equation and solve for either one of those variables. It doesn't really matter. And then we can go and plug that back in. But just for the sake of us needing to do elimination in the very near future, let's do elimination. So if we call this equation 1, whoops, and we call this equation 2, we want to eliminate one of these variables. Well, we've got a couple options here. Well, exactly two options, right? We want to either eliminate the x's or we want to eliminate the y's. And in your work, you're going to want to choose the easy thing to do. So I don't know, this is going to be kind of a toss-up for what the easy means to you. Usually easy means small numbers, positive numbers, no fractions, right? That's usually what easy means. But, you know, easy can mean different things to different people. For example, here we could say that, hey, that's going to be easy if I add 3 times equation 2, right? So if I write that, 3 times equation 2, and if I add that to equation 1, what are we going to get there? So 3 times equation 2, I would have a 3 here, a 3 here, and a 3 here. And then we would add them all up. So we've got 0 x's. Adding up on those x's, we get 0. Add these guys now, we got 4y. And then we add these, we get 16. All right. Well, we've eliminated x. That's great. Now I can solve for y. So y is 16 over 4, which we know is just 4. Now at that point, we've got that y value, and we can plug it into either one of these equations, which, you know, the second one's probably going to be the easiest to do, right? X plus 4 equals 1. That's going to tell us that x is negative 3, and our solution is negative 3 comma 4. Boy, that's ugly. Negative 3, 4, comma. Okay, so there's our solution there. And we did that with elimination. So we can do the same process for these others, right? Probably let's choose elimination because it's usually the easiest thing. So with this one, what do we want to do? Maybe we can do, if I call this equation 1 and I call this equation 2, we can do negative 5 times equation 1 and add that to equation 2. So if we have, and maybe I'll just stack that up right underneath this. So negative 5 times equation 1, I would have negative 10x. Negative 5 times negative 1 would be plus 5y. And then 1 times 5 is negative 5. Okay, so that, we put that one right here. And then we've got equation 2. We didn't change it. And now what happens when we add these together? Well, on the left-hand side, well, we got 0, right? 0x and then 0y. And on the right-hand side, well, we've got zeros again. So what this is going to indicate to us is that there are a bunch of solutions to this. This is in our previous example where we had 0 equals 0. This was called an identity, and we had that all the real numbers were solutions. But in this case, that's not going to be exactly what we're talking about here. All the real numbers are not solutions because our solutions are ordered pairs, aren't they? So we're not going to have all the real numbers be solutions. And thinking about this further, if we were to draw a picture of this, maybe we're not exactly sure what the lines look like, but what we could do is we could take equation 2 and divide all these by 5. Divide both sides by 5. And isn't that the same as this? Well, what happened here is that if we draw this line and draw that line, they're the same line, right? They're the same line. So yeah, if that happens, we've got infinitely many solutions. So the difficulty here is going to be to express yourself as something that's not just saying all the real numbers are solutions. We need to write an ordered pair so that the ordered pair is going to give us our solutions. So we need to know, well, what do we put there? Something that we're going to want to do is choose one of the variables to act as kind of a dummy variable, because it doesn't really matter what one of the variables is. As long as if we choose a single value, like for example, if I picked x equal 1, I could find a y value that goes with it, right? And that's going to be part of my solution set. Well, if I took and solved this for y, then we could write if we add y to both sides and subtract that 1, we would have y equal 2x minus 1. So if I choose any number I want at all for x, no matter what I choose, that y value is going to be determined by that relationship, 2x minus 1. We could have just as easily done this with the y instead. So if I, just to be clear about what I'm saying here, if we took and instead solved for x, we could have, x would be add y to both sides. So we got 1 plus y, and then divide both sides by 2. So there you go. Now I can write my ordered pair as y, and now I choose anything I want for y, and then the x value is going to be that one. So depending on which variable you want to be the free choice, we can write it either with x as our free choice, or we can write it as having y as our free choice. Doesn't really matter. Okay, so this next one here is going to be a little quicker than this, because we won't have to multiply by anything. And we could probably just eyeball it a little bit and say, oh, look, all of the coefficients are already what we want. If I add both sides together, I'm going to have 0 on the left, and I'm going to have 3 on the right. Now, this is never true, and this one's going to have no solutions. And that's going to be the easier case between these two, is when we have no solutions, because we don't have to express infinitely many points that are solutions, because, well, there are none. Okay, so yeah, we classify systems of equations as either consistent or inconsistent. So consistent means it has a solution, and inconsistent means it has no solution. Dependent means it's the same line, dependent means it's the same line. Independent means we have two different lines. So if we were to draw pictures of this, consistent system is going to have a solution. So if I drew my lines, I would have, hey, there's a point right there where they intersect, and that's going to represent your solution. If we have no solution, well, that's going to be two parallel lines, right? They're never going to touch. They're not going to intersect. If they're dependent, this means that they're the same line. So we've got one line here maybe and another line just right on top of it. And then independent means that they're different lines. So we can use these words to classify our systems, if we have solutions or not, and if they're the same line or not. Okay, so we have an application problem. So application problems in these sections are going to be no real difference from what we've already seen. We still want to, read the problem and understand what they're asking. And then we want to write math stuff that models the problem. So we're just going to have two statements that we're going to have instead of one that we usually have. Okay, so here we have a buffet. They charge $7.50 for a child and $9.25 for an adult. Got a group of 27 people eating at the buffet. Their total bill was $227. Okay, so how many of each were there in the group? Okay, so yeah, our first step is to identify what's unknown. So we don't know how many children, we don't know how many adults. So maybe let's just say C is the number of children, and let's say A is the number of adults. Okay, and now we want to come up with an equation or two that's going to model the problem. Okay, so if a group of 27 people, we know that 27 people came, so our group is going to be consisting of adults and children. So wouldn't it be true that adults plus children is 27, right? There's 27 people. And now we want to maybe, so here we modeled how many people there were. And maybe we could say that that's, an amount. And our next equation here is probably going to be based on the cost, right? So how much is this side of the equation going to cost? Well, our adults are $9.25 per adult, and our children are $7.50 per child. And I know if I add all that up, we've got $227. Okay, so this was based on our total cost on each side. And we can write that as a price, right? A price. So, hey, we look at that. We've got a nice system of equations. Now, the difficulty of this problem really is just finding our system to go and solve, because we can go and solve this system using the methods we talked about above, or we could use the method that we're going to talk about below here in a second. But anyway, solving this equation, or excuse me, solving this system isn't really the focus right now. We just want to set it up because, we can find a solution to this. Okay, so when we have percentages in here, things fall apart. Like these are somehow a bit more difficult. But I know I'm not sure how much meaning my statement will have, but this one really isn't any different than the one above it. So we got a 10% salt solution. We're going to mix it with pure water to get 75 gallons of a 3% salt solution. So how much of each are needed? Well, we can do this the same way, right? So we're going to add some salt. We're going to add some water. Let's say S. Let's say that is the number of gallons of salt solution. Well, that's a 10% salt solution, right? And let's say that W is number of gallons of the water. And this is a 0% solution. Okay, well, we're going to have one equation here that we can model just like we did above by the total amount. So we want 75 gallons. So we have to have S plus W equals 75, right? If I'm going to have 75 gallons, when I end it up, I'm adding a salt solution to water, and, well, I've got to get 75 gallons. Now, our next equation is going to be the total, not cost on each side, but the total concentration. So this is based on an amount, and our next one is going to be a concentration. So how much salt? So how much salt is there in there? Okay, well, we've got that our salt solution has 10% of that is salt. So we can put 0.1 S. That's going to give us the amount of salt in the salt solution, right? 10% of whatever the gallon amount is going to be just salt. Well, our water has no salt in it. So we got 0 times W. And then on our right-hand side, we want 75 gallons of a 3% solution. So we got 0.3 times 75. Okay, well, now we have our system of equations here, and we can solve that system of equations using either the method above, or we can use the method that we're about to talk about here real quick. So great, this was the difficulty of the problem, and just pro tip here, one of our equations is pretty much always going to deal with an amount or a total amount of something, and then the second equation, we're going to be talking about a concentration, or we're going to be talking about a price. So we want the price on each side, or we want the concentration on each side, like how much salt is there, right? Okay, great. So now we get to make it just a little more difficult. So a linear equation in n variables, so more than 2, is an equation of this form where all a's and c's are real and at least one of these a's is not 0. So usually we're going to have, our variables are going to be x, y, z, or they're going to be w, x, y, z. Maybe they'll be a, b, c, d. We have to use these subscripts in our definitions because there could be more variables than there are letters in the alphabet. So that's something we've got to take into account. Okay, so yeah, so an example here, maybe 2a plus 3b minus 4c plus 5d equals 9. There's an example, right? We've got a linear equation in 4 variables here. Okay, so we're going to have to do systems of equations with more than 2 variables, and what we're about to say here, these are really just reorganizations of those substitution and elimination methods. So, right, we can add the same thing to both sides of an equation, and it's still the same thing. And we can switch places, and it's still the same. So interchange the position of any 2 equations. We're just trading their places. We can replace an equation with a non-zero multiple of itself, right? If I have that a equals b, then that means that a times c is the same as b times c, right? As long as c is not 0, that's true. Replace an equation with itself plus a non-zero multiple of another equation. So this is what we're going to be doing most often, replacing equations with equivalent equations. Once we get going with this, and once we do a couple examples, these things will be a little more clear. Here we have triangular form definition. So we're going to have pretty much all the homework problems are going to have you put the systems in triangular form. So this is what triangular form means. So the subscript of the variables in each equation increase from left to right, or they're in alphabetical order. That's what we're going to see most often, alphabetical order. Okay, the leading variable in each equation has coefficient 1, so it's just an a, or it's just an x, or it's just y. Its leading coefficient is 1. The subscript on the leading variable in a given equation is greater than the subscript on the leading variable in the equation above it. Or to phrase this with letters, each row as we go down, we're going to be removing the letter before it. So let me write an example. So maybe a plus b plus c equals some number. In our second equation, it's just going to have b plus some number times c, and then our third equation is just going to have c, right? So we're going to have 0 a's in this one, we're going to have 0 a's in this one, and 0 b's in this one, and then all the way down the line. So when we have zeros in these positions, they're really not there, and this is going to kind of triangular form, right? It looks like a triangle. So going down the line here, we're removing variables. Okay, any equation without variables cannot be placed above an equation with variables, so these go on the bottom. So yeah, equations with variables are going to look like 2 equals 2 or 0 equals 0, something like that. Okay, so let's actually do this. So we want to write this system here below in triangular form and solve if possible. Now something that I didn't say here is the beauty of this triangular form here is that bottom row, we're just going to have c equals some number, and we're going to have it. There it is. C is some number. And then we can take and substitute back into the others to find the other variables. So let's actually look at this with an example. And, well, we can go for it. So, or organization is going to be a really, really, really big deal on these. So be real careful that you're noting what you're doing in each step so that you can be clear about what that is. So let's call this 1, 2, 3. So now we're going to change the system. Let me put my little curly bracket on there. So our first goal is to get a 1 in that position right there. And we have the moves that we're allowed to do up from above. We could just multiply row 1 times 1/3, and then we're going to have a 1 in that position, right? But that's probably not going to be the easiest thing we could do, because we're going to have, if I multiplied everything by 1/3, I would multiply those two guys by 1/3 as well, and then I'm going to have a bunch of fractions, and we really don't want to do that if we don't have to. So the easier thing to do would probably be to take row 1 and subtract row 2 and replace row 1 with that. So we are replacing a row with itself plus a non-zero multiple of another row. That was one of the legal moves we can do. So row 1 minus row 2, we're going to put that in place of row 1. Okay, so row 1 minus row 2. So we got 3 minus 2 would just be 1x. We would have these two subtracting, right? Negative y minus 3y. We would have minus 4y. And then finally here, z minus negative z. So that would be 2z. I guess not finally, because we still have these guys, right? 3 minus 1, that's 2. Okay, so we didn't change anything about the other ones. So we've got 2x plus 3y minus z equal 1. We've got 2x minus 4y plus 3z equals 16. All right, so there's our new little system here. Well, it's not a new system, it's an equivalent system. Okay, so now that we have a 1 in this position here as our coefficient, we want to make these guys zeros. So, well, we can do that. And let's call this 1, 2, 3 again. So now we can use, since I've got a 1 in this position, I can use a multiple of that row to knock out the others below it. So if we take row 2 and subtract off 2 times row 1, we're going to put that in place of row 2. And why don't we do the same thing with row 3? So we can take row 3 and subtract off 2 times row 1 and put that in place of row 3. Okay, so that's our whole step. So row 1 is not changing. We're going to leave it be. So we got x minus 4y plus 2z equals 2. And now we have these other guys that we need to deal with. So let's do that. We can just do what we have prescribed over on the left. All right, so we're going to take row 2, which is this one, and we're going to subtract 2 times this one. So we've got row 2 is 2x minus 2 times row 1, so that's going to be, well, 2 minus 2 is going to give us 0, which is exactly what we wanted. So, I mean, maybe we can just write that in there just to be complete. Maybe we don't have to carry that 0 forward in the future steps, but let's just write it there for now. Okay, so now we've got, again, we're doing row 2 minus 2 times row 1. So row 2 here is a 3 in the y position, and subtracting 2 times row 1, we're going to be adding 8. So that's going to give us plus 11y, right? 3 minus negative 8. Wait. Excuse, yeah, 3 plus 8 is going to be 11, right? Because negative 2 times negative 4 is positive 8, and we add those together. Okay, and then the z position, we've got negative z minus 4z, so that's negative 5z. Okay, and then the 1, we've got 1 minus 2 times 2, so that's 1 minus 4 is negative 3. Okay, so now we've eliminated that eliminated the x term, and we are still on our way here. Okay, so now we've got the third row. we're going to take row 3 minus 2 times row 1. All right, let's do it. So row 3 in this position has a 2. Minus 2 times row 1 would give us 0. Okay, so now we've got negative 4 in the y position. Minus 2 times row 1. So that's going to be negative 2 times negative 4 would be positive 8. So adding 8, we're going to have plus 4y. Okay, and then we've got 3z minus 2 times this one. So 3 minus 4 would be negative 1. Okay, good. And now what? The constant. So we've got 16 now in that position. Minus 2 times 2. So that's going to be 16 minus 4 would be 12. Okay, great. So now we are almost there. We now need to get a 1 in this position here, and we can do that. You know, something that would be easiest would just be to interchange rows 2 and 3, right? Because then all we have to do is divide this one by 4, and then we're going to have a 1 where we want it. So let's do that. So all we're doing is interchanging rows 2 and 3. Okay, row 1 stays the same. Rows 2 and 3 are going to change places. So I got 4y minus z is 12. And we've got 11y minus 5z is negative 3. All right. So now, essentially, we're done with the first equation now because that has an x in it. And if we combine that with any of the other two, we're going to be introducing that x back in there, and we really don't want to do that. So yeah, let's get rid of this 4 in that position. We can just replace row 2 with 1/4 times row 2. Okay, so row 1 is the same, so x minus 4y plus 2z equals 2. And then 1/4 times row 2, we got 1y minus 1/4 z equals what? 12 divided by 4, that's 3. And then we've got 11y minus 5z equals negative 3. And now we can just use this row to get rid of that y in this position. Okay, so let's do that. So we can take row 3, if we call that again 1, 2, 3. I can take row 3 and subtract off 11 times row 2. Put that in place of row 3. Okay, so our first row isn't changing, it hasn't changed for a while, and that's okay. Our second row, that's not going to change either because we've got a 1 in that position, just like we have a 1 in the position with the x in the first one. Okay. And now our third equation is going to change, right? So by design here, row 3 minus 11 times row 2, those are just going to go away. We're going to have a 0y there. And now we can do what's in the z position. So I've got row 3, which has negative 5. We want to subtract, so minus 11 times this one. We probably want to do a little bit of scratch work here. So we want to do minus 5 minus 11 times minus 1/4. So this is minus 5 plus 11/4. Well, we know that minus 5 would be 20/4, right? Plus 11/4. So this will be 9/4 negative. Okay, and we can write that in. So we got minus 9/4 times z equal, and then we want to do a little bit of scratch work to find that constant. right? Okay, so now we're doing the constant. So we've got -3 minus 11 times, well, 3. So we've got -3 minus 33, which would be -36. Okay, so at this point, we've got a 1 in this position, a 1 in this position, and nothing below, and nothing below. And now we just need to get that to be a 1. So this is going to be just a one more step kind of deal. If we call that 1, 2, 3, we can just take 4/9 negative times row 3 and replace row 3 with that. And that's going to get rid of all of our, well, it's going to get rid of the coefficient in front of the z. So row 1 stays the same. We got 1x minus 4y plus 2z equal to. Row 2, we've got 1y minus 1/4 z equals 3. And now row 3, we're going to replace it with -4/9 times row 3. So that we're going to have a 1z there. And now we have to do, what is this? -4/9 times 36. So 36 divided by 9, we know that that's 4. Times 4 would give us 16. Okay, and now, lo and behold, the left side with all the variables looks like a triangle, right? And we have triangular form. When you type these in, when you're in WebAssign typing these in, it's going to ask you to do this in a comma-separated list. So we'll type the first row and then a comma, then the second row, then a comma, then the third row, and then if there's a fourth row, we're going to have another comma there. But on paper, hey, look, it looks like a triangle. That's wonderful. Now the beauty of this is that one of our variables is solved for, and now I can take, now that I know that that's 16. I can put z equals 16 back into row 2. So we can write that out, and we can come up with a solution really quickly. So row 2 is y minus 1/4 times z equals 3. So I got y minus, what is this? 16 divided by 4 is 4, equals 3. So that means y is 7. Okay, that's great. So we got z is 16, y is 7, and plug them both into there. So we got equation 1 now. We can put both of those in there. So we've got x minus 4 times y plus 2 times z has to be 2. And we can solve this. We've got x minus 28 plus 32 equals 2. So adding these guys together, we got x plus 4 equals 2. So that tells us that x is -2. That's wonderful, right? Because now we have the values of all of these variables. And we can say that the solution to the whole system is the ordered triple, -2, 7, 16. Now, if we're not just completely rock solid confident in this, we just go plug it back into the original equations and we can show ourselves that it makes it true. Okay, great. So admittedly, there aren't all that many examples in this video, so I'm going to tack a few more examples onto the bottom of the Canvas page. So check those out. Anyway, thanks for watching this video, and let me know if you have any questions, and have a wonderful rest of your day.